We shall now move on to the next topic in the preliminaries, which is functions. Suppose we have two sets A and B. A function f from A to B is a rule which assigns to each element of A a unique element in B. That means if x is an element of A, then f takes this x and assign it to an element, a unique element in B. So as f takes x and assigns it to this element in B, this element in B is denoted as f of x and is called the image of the point x under the rule f. Okay, so f is a function if f takes all the elements of A and assigns it to some of the elements of B. Okay, so it is not necessary that all the elements have different images. So it is also possible that two elements in A can have the same image in B. But an element in A will not have two images in B. So this will not happen. This can happen. So a function f from A to B is a rule which assigns to every element of A a unique element in B. Now, if f is a function from A to B, then the set A is called the domain of the function f. Domain of f. And B, the set B is called the codomain of f. Now, if we take all the elements of B, which are images of some of the elements of A, then that set is called the range of f. It is not necessary that all the elements of B are images of some elements of A. So there can be elements in B which are not images of any element of A. So in that case, range of f is the set of all elements which are images of elements of A. So we can see that range of f is always a subset of B. Okay, it can be B also, but it is not necessary that it should be B always. Now, to put it formally, given two sets A and B, a function f from A to B, a function from A to B is a rule or a mapping that takes each element x in A and associates with a single element of B. In this case, we write f from A to B. I forgot to tell you this. If f is a function from A to B, we write it as f from A to B. Now, given an element x in A, the expression fx is used to represent the element of B associated with x by f. That means fx denotes the image of x under the function f. A set A, the set A is called the domain of f, and the range of f is not necessarily equal to B, but it refers to the subset of B given by set of all y element of B such that y is equal to f of. That means this is the definition for range. A range means the set of all y elements of B such that y is equal to f of x. That means y is the image of some x in the set A. Now we shall see some examples for functions here. The first example is given as g of x is equal to set of all, or g of x is equal to 1 if x is an element of q. Q means the set of all rational numbers, and 0 if x is not an element of q. That means x is not a rational number, which means x is an irrational number. So when x is a rational number, g of x will be 1, and when x is an irrational number, g of x will be 0. For example, g of 3 by 2. 3 by 2 is a rational number, so g of 3 by 2 will be 1. G of 9 by 4 will be 1. G of 5 will be 1. But g of root 2, as root 2 is an irrational number, g of root 2 will be 0. G of pi will be 0. G of root 3 will be 0, like that. Okay, so g of x. So you can see that g of x is defined to be 1 for all rational numbers, and defined to be 0 for all irrational numbers. So g of x is defined for all rational numbers with value 1, and g of x is defined for all irrational numbers with value 0. So g of x is defined for all the real numbers. So the domain of g of x is R. Okay, or the domain of the function g is R. Now, when you look at the range g of x, if x is a rational number, then the image is 1. If x is an irrational number, then the image is 0. So no other number will be an image of any of the x in R. So the range of f is just the set 0 and 1. 0, 1. Now we shall see another example. So in the next example is for the absolute value function, or the modulus function, defined as modulus of x. So modulus of x is defined as x if x greater than or equal to 0, that means x is positive or 0, and minus x if x is less than 0, that means x is negative. So if x is negative, then value of modulus x, or absolute value of x, will be minus x, and if x is more than or equal to 0, greater than or equal to 0, then absolute value of x will be x itself. Now we shall see some important properties of the absolute value function, or the modulus function. The first one being modulus of AB is equal to modulus A into modulus B, and the second one is modulus of A plus B less than or equal to modulus A plus modulus B, whatever be the values of A and B. Now the second property, modulus of A plus B less than or equal to modulus A plus modulus B, is called the triangle inequality. Now we shall see some questions. The first question being, verify that modulus of AB is equal to modulus A into modulus B for all values of A and B. That is the first property here. And to prove this property, we use the fact that square root of x square is equal to modulus x for all real values of x. Now for any real numbers, we have AB the whole square is equal to A square into B square. That is a property of exponents. AB the whole square is equal to A square into B square. Now take square root on both sides. So you'll get square root of AB the whole square is equal to square root of A square B square. Now the left side, square root of AB the whole square. Using this property, square root of x square is equal to root x. Using that property, you will get square root of AB the whole square is modulus of AB. And square root of A square B square, you can write it as square root of A square into square root of B square. That is a property of square root. Okay, and square root of A square is modulus A, and square root of B square is modulus B. So we get this result, modulus of AB is equal to modulus A into modulus B, whatever be the values of A and B. Now we shall move on to the next question. Verify the triangle inequality. Modulus of A plus B is less than or equal to modulus A plus modulus B for all values of A and B. So we start with the identity A plus B the whole square is equal to A square plus 2AB plus B square for all values of A and B. Now we know that modulus of A the whole square is equal to A square, because by the definition of the modulus function, modulus of x is equal to x if x is greater than or equal to 0, and this is equal to minus x if x is less than 0. Okay, so if A is positive, then modulus A will be A. So modulus A the whole square will be A square. And if A is negative, then modulus A will be minus A. So modulus A the whole square will be minus A the whole square, which is again A square. Okay, so I am replacing A square with modulus A the whole square and B square with modulus B the whole square. So this will become mod A the whole square plus 2AB plus mod B the whole square. So now we know that A is less than or equal to mod A. So if A is positive, then A modulus A is same as A. So this will be equal to when A is positive. Now when A is negative, for example, A is minus 3. So here we will get minus 3, and this will be mod of minus 3, which is 3. Okay, so here we can say that A is less than mod A. So anyhow, combining both the cases, we will have A is less than or equal to mod A. So what I do is that I replace this A with mod B and A with mod A and B with mod B. So this equal to will become less than or equal to, because of this result, A less than or equal to mod A. So this will become mod A square plus A replaced with mod A and B replaced with mod B plus mod B square. So you can see that this is mod A square plus 2 mod A mod B plus mod B square, which is mod A plus mod B the whole square. So what we have got is that on the left hand side we have A plus B the whole square, and right hand side we get A plus B the whole square less than or equal to mod A plus mod B the whole square. So taking square root on both sides, we'll get modulus of A plus B the whole square is less than or equal to modulus of A plus modulus B the whole square. So we know that root of x square is modulus x. So square root of A plus B the whole square is modulus of A plus B, and square root of mod A plus mod B the whole square is modulus of mod A plus mod B. And modulus of, since modulus A and modulus B are positive, modulus A plus modulus B will be positive. So the modulus of that positive quantity will be same as modulus A plus modulus B. Okay, because if 3 is positive, modulus 3 is 3 itself. Since 3 is positive, modulus 3 is 3 itself. So modulus of a positive quantity is the same quantity. So modulus A plus modulus B is a positive quantity. So the modulus of that is equal to modulus A plus modulus B. So what we got here is that modulus of A plus B is less than or equal to modulus A plus modulus B, which proves the triangle inequality. Here we have a remark which says that given 3 real numbers A, B and C, we have modulus of A minus B. A minus B can be written as A minus C plus C minus B. So this plus C and minus C are added and subtracted here. So if I consider this A minus C as X and C minus B as Y, this is modulus of X plus Y, and using the triangle inequality, this is less than or equal to modulus X plus modulus Y. So Using the triangle inequality, I can write it as less than or equal to modulus of A minus C plus modulus of C minus B. That is what we got is modulus of A minus B on the left side is less than or equal to modulus of A minus C plus modulus of C minus B, where A, B and C are any real numbers. Now we will extend this result a little further. We have a question here. Prove that modulus of A minus B is less than or equal to modulus of A minus C plus modulus of C minus D plus modulus of D minus B for all values of A, B, C and D. Now we start with modulus of A minus B on the left side. So modulus of A minus B is equal to, as before, we'll write it as modulus of A minus C plus C minus B. And using the triangle inequality, this will be less than or equal to modulus A minus C plus modulus of C minus B. Okay. Now we will keep the first modulus as it is, and in the second modulus C minus B, we will subtract and add D in between C and B. So this will become, this is equal to modulus of A minus C plus the second one, modulus of C minus B, can be written as modulus of C minus D plus D minus B, where D is any real number. Now what we do is that we apply the triangle inequality for the second modulus. So this can be put as less than or, first will be as it is A modulus of A minus B, modulus of A minus C. So you'll get less than or equal to modulus of A minus C plus this is less than or equal to C minus D plus modulus of D minus B, using the triangle inequality again. So on the left side we have A minus B, modulus of A minus B less than or equal to modulus of A minus C plus modulus of C minus D plus modulus of D minus B for all real numbers A, B, C and D, which is the required result. We shall now move on to our next question. Prove that modulus of modulus A minus modulus B less than or equal to modulus of A minus B for all A and B. Now for all A and B, we can write modulus of A is equal to modulus of A minus B plus B. And using the triangle inequality, you will get this is less than or equal to modulus of A minus B plus modulus of B. Now if you move this modulus of B to the left side, you will get modulus A minus modulus B less than or equal to modulus of A minus B for all values of A and B. Now similarly, we can write modulus B is equal to modulus of B minus A plus A. So using the triangle inequality, you will get this is less than or equal to modulus of B minus A plus modulus of A. Now modulus of B minus A is the same as modulus of A minus B. So replacing modulus of modulus of B minus A with modulus of A minus B, we will get this is equal to modulus of A minus B plus modulus of A. Now move this modulus of A to the left side, you will get modulus of B minus modulus of A is less than or equal to modulus of A minus B. Now earlier you got that modulus A minus modulus B is less than or equal to modulus of A minus B. Now you got that modulus of B minus modulus of A is less than or equal to modulus of A minus B. So you can see mod A minus mod B less than or equal to modulus of A minus B, and mod B minus mod A less than or equal to mod A minus B. So from here you will get that modulus of this quantity, if this is positive, this will be negative. If this is negative, then this will be positive. So from both you can write that modulus of mod A minus mod B is less than or equal to modulus of A minus B. We shall now move on to the next question. Given a function f and a subset A of its domain. So if you are given a function f and A is a subset in the domain of f, and let fa represent the range of f over the set A. So here you have a domain of f, and inside the domain of fa is a small set. Okay, now the set of all images of the elements of A under the function f is denoted as fa. Okay, so that means fa is equal to the set of all f of x says that x is an element of A. That means it is the set of all images of the elements of the set A. Now part A, you are given f of x is equal to x square and A is equal to 0 2, closed interval 0 2, B is equal to closed interval 1 4. You got to find fa and fb, and you have to check whether f of A intersection B is equal to f of A intersection f of B in this case. And also you have to check whether f of A union B is equal to f of A union f of B in this case. Now the part B, find two sets A and B for which f of A intersection B not equal to fa intersection fb. Okay, look at case A. From here you are given A is closed interval 0 2 and B is closed interval 1 4. Now if you take the union of A and B, so A is closed interval 0 2 and B is closed interval 1 4. So A union B will be starting from 0 to 4. So closed interval 0. Now A intersection B, the common region to these intervals 0 2 and 1 4 is 1 2. Okay, closed interval, you can check. This is 0, this is 4, this is 2, and this is 1. Okay, so A is 0 2, this is A, this is A, and B is 1 4, so 1 4, this is B. So union means you got to combine these intervals, so you'll get 1 4 starting from 1 till 4, so closed interval, sorry, starting from 0 to 4, so that is a closed interval 0 4, and A intersection B means a region common to both the intervals, which is in between 1 and 2. So A intersection B is closed 1 2. Now f of A, so you can see that f of x is x square. So f of A is a closed interval 0 2, so it is a continuous interval, so you have all the points in between 0 and 2. So if you f of A will be the square of all the points in 0 2, closed interval 0 2, so which you will get 0 4. Okay, the square of 0 is 0 and square of 2 is 4, so you'll get the closed interval 0 4. And f of B is the square of the interval 1 4, which you will get it as 1 closed interval 1 16. Now f of A union B, f of A union B is 0 4, so f of A union B will be the square of the end points of the interval, which is 0 16, and f of A intersection B, as A intersection B is 1 2, f of A intersection B will be 1 4. Now we have to verify these things. So the first part of the question was to find fa and fb. We have found fa and fb. Now you got to verify that f of A intersection B is same as f of fa intersection fb, and also you have to verify that f of A union B is equal to fa union fb. So you have got fa and fb. We'll find the union of both. fa union fb, fa union fb, fa is 0 to 4 and fb is 1 to 16, so fa union fb will be closed interval 0, 16. And also FA intersection FB, that means the common region for the closed interval 0, 4 and closed interval 1, 16 will be closed interval 1, 4. So now you got to check whether this is true. What is f of a f of a intersection b? F of a intersection b is 1, 4, closed interval 1, 4, and f of a intersection f of b is also closed interval 1, 4. So you can see that both are same. So we can say that f of a intersection b is equal to f a intersection fb. And also we have to verify the other thing, f of a union b. Just a minute. F of a union b is closed interval 0, 16, and fa union fb is also closed interval 0, 16. So you can say that both these are same. So f of a union b equal to fa union fb. So this proves the first part of the question. And for the second part, find any two sets A and B for which f of A intersection B is not equal to FA intersection FB. So we have to choose A and B in such a way that f of A intersection B will not be equal to FA intersection FB with the function f of x is equal to x square. Okay, now we will take A as 0, 3 and B as minus 2, 0. So if we take A as 0, 3 and B as minus 2, 0, FA with this function f of x is equal to x square will be 0, 9. And FB will be square of this is 4, square of this is 0. So it will be the interval 0, 4 FB. Also, A intersection B. A intersection B, if you mark it on a number line, A is this is 0, A is 0, 3, this is 3. So this is closed interval 0, 3, and B is minus 2, 0. So this point is minus 2, and B will be this interval, closed interval minus 2, 0. Now if you check the intersection of A and B, there is only one point which is common to both the intervals, and that point is 0. So you'll get A intersection B is equal to singleton 0. And if you and f of A intersection B, that means f of 0. So as f of x is x square, f of 0 will be 0 square, so it is again 0. Okay, so f of A intersection B is singleton 0, so f of 0 will be again 0. So you'll get f of A intersection B is equal to set 0. Now you can see that f of A intersection B, here you got it as singleton 0. FA FB, FA is 0, 9, FB is 0, 4. So their intersection FA intersection FB will be 0, 4. One is 0, 9, another one is closed interval 0, 4. So the common region for both is closed interval 0, 4. Now you can see that FA intersection FB is not equal to f of A intersection